In this video, we will explore the Fourier series. The Fourier series decomposes a periodic signal into a summation of sinusoids. The main idea is that while an arbitrary signal may be difficult to analyze, a linear summation of sinusoids is much easier. Therefore, if we can effectively break down a signal into a linear summation of sinusoids, we can perform complicated analysis in a much more straightforward manner. In this video, we will see how to obtain the Fourier series of a periodic continuous time signal and what it means. The first thing that we have to do is to define the notion of the fundamental frequency of a periodic signal. Given a periodic signal, such as a pure cosine, something like this, we know that its period is going to be the time that it takes to fully repeat, and we can define that as t0, which corresponds to a frequency omega 0 of 2 pi over t0. In this case, the fundamental frequency omega 0 is the only frequency in the signal and is therefore easy to find. For an arbitrary signal that is also periodic, perhaps something like this, we can also define a fundamental frequency as the frequency at which the entire signal oscillates, as opposed to the individual components that make it up. So we can find 2 points that are the same, and we can define that as the fundamental period, which corresponds to the fundamental frequency of 2 pi over t0 once again. In general, for any periodic signal, we can find the fundamental frequency as the frequency at which the entire signal repeats itself. As I mentioned in the introduction, if we want to express a periodic function as a sum of sinusoids, which is our goal with the Fourier series, we must ensure that the sum of the sinusoids has the same periodicity as the periodic function that we are trying to express. If the function that we are trying to express has a period of t0, then we know that the slowest sinusoid that we could possibly use to represent it is going to also have a period of t0. So we'll draw something like this, and we can define the period as before as t0 over here, which corresponds to a fundamental frequency of 2 pi over t0. Now we can use higher frequencies to create our more complicated signal as a weighted summation of these sinusoids, but the other sinusoids have to obey a specific property. So let's take another one of these, maybe something like this. It's at a higher frequency than the previous one, and if we look at its period, let's call it t1, it's going to be 1/2 of t0, which means that its frequency is going to be twice the frequency of this signal over here. And if we take another one at an even higher frequency and look at one of the periods, t3, it has to be 1/3 of t0. In other words, its frequency is going to be 3 omega 0. Now you can see that each one of these is at an integer multiple of this first fundamental frequency, which was the frequency of oscillation of the entire more complicated signal that we're trying to represent as a summation of these sinusoids. This is because if the frequencies of the components were not at integer multiples of the fundamental frequency, then the entire composite signal would not have the same periodicity as our original signal that we're trying to recreate. And since we know that we have to have the same frequency of the summation of these sinusoids as the original periodicity of the more complicated signal, we have to use sinusoids which are at integer multiples of the fundamental frequency, which is again defined as the frequency of the overall signal. With that in mind, we're ready to look at the actual Fourier series. The Fourier series says that a periodic signal x of t can be written as an infinite summation of scaled complex exponentials. And this is the form that we're going to use, where once again omega naught, omega 0, is equal to 2 pi over t0, where t0 is that fundamental period or the periodicity of the overall signal x of t. And basically what we're saying is that x of t is now going to be a summation of complex exponentials that are weighted by these constants c sub k, which can be complex. Now the complex exponential is nothing more than sinusoids as related by Euler's identity. And therefore, this is exactly what we had said previously, that we can represent a signal x of t, which is periodic with period t0, as a weighted summation of sinusoids. This is just putting it into a slightly different form, which is better for analysis. And to find each one of the c sub k's, we perform an integration over one period of our signal of x of t times e to the minus jk omega naught t dt. These two equations are very important, and the first one is called the synthesis equation, and the second one is called the analysis equation. This is the analysis because it breaks down the signal x of t into these Fourier coefficients c sub k, whereas the synthesis equation takes the Fourier coefficients and recreates our original signal x of t, or synthesizes it, out of the complex exponentials that are scaled by the Fourier coefficients. As I mentioned, c sub k is a complex quantity. That is, it has an amplitude and it has a phase. It can be represented in this kind of a notation since it's a complex number. So it has this amplitude and it has a phase. And to better understand what these various components are, the amplitude and phase, we can rewrite x of t in a slightly different form. So we can take x of t, and as I mentioned, we can relate things using Euler's identity. So we take our summation and we rewrite it as the amplitude c sub k e to the j phase c sub k. So this is just what we had right here, replacing c sub k with this notation, times e to the j k omega naught t. So this is just the second part over here. So we just rewrote x of t with this new notation, and we can combine some things. So it's still the summation times the amplitude of c sub k. These two exponentials can combine to form e to the j k omega naught t plus the phase of our complex value c sub k. And now, as I mentioned, using Euler's identity, we can rewrite this as the amplitude of c sub k times cosine of k omega naught t plus angle k, c sub k, plus j sine of k omega naught t plus angle c sub k, just by using Euler's identity. So we can see clearly here that x of t is being represented as a summation of sinusoids with some complex values that are happening in here. But these are going to cancel out properly with a good choice of c sub k, which we're going to see in some examples, in order to get a real signal for x of t without any of these imaginary components. But what you can see here is the importance of the amplitude component of c sub k and its phase. The amplitude basically tells you how much of a particular cosine or sine of a particular sinusoid you have in your signal. And the angle tells you basically where to place these individual components, since it tells you the phase offset of each of these components. Now, what are these actual components? They're just cosines and sines at integer multiples of the fundamental frequency. And remember what we said earlier, that in order to create a given signal with a periodicity of t0, we need to use component sinusoids in the summation that are going to be at integer multiples of the fundamental frequency, omega 0. And that's exactly what we have in our synthesis equation here. We have a summation of these complex exponentials, which is nothing more than sinusoids, at integer multiples k times the fundamental frequency, omega 0. So that's exactly what we have here, and this shows us that we can see that we are adding how much of a particular sinusoid at a given integer multiple of the fundamental frequency, and the angle tells us where to place it relatively to the origin in order to recreate our original signal. Now let's illustrate this idea through some examples. We'll start off with a periodic signal, which is itself going to be just a cosine. Cosine of 10 pi t minus pi over 3. So very directly, we can see that the fundamental frequency is just going to be 10 pi, since that is the only frequency in this signal. There are no other components. We can break this down using Euler's identity into a summation of complex exponentials without performing any integration or anything like that, as we had said in the analysis equation, but simply using the identity, we get that this is equal to 1/2 e to the j 10 pi t minus pi thirds plus e to the minus j 10 pi t minus pi thirds. We can further rewrite this as 1/2 e to the j 10 pi t times e to the minus j pi thirds, just using properties of exponentials. And likewise, distributing the 1/2, we get plus 1/2 e to the minus j 10 pi t, again splitting up the exponential, e to the positive j pi thirds, since we had a minus j and a minus pi thirds here. Now rewriting this once more, I'm just going to regroup things, and I have 1/2 e to the minus j pi thirds times e to the j 10 pi t plus 1/2 e to the j pi thirds e to the minus j 10 pi t, simply rewriting the previous equation in a slightly altered form. Now, let's go back to our synthesis equation. We know that x of t is equal to the summation from k equals minus infinity to infinity of c sub k e to the j k omega naught t. Well, this is nice because it looks just like what we had over here. It has the exact same form. And if we write out a few of these terms, we'll skip from negative infinity up to c of minus 2. We pick k equals minus 2 over here. E to the j minus 2 omega naught t, so that's the negative 2 term of this summation, plus c sub negative 1 e to the j minus 1 omega naught t plus c0 plus c1 e to the j 1 omega naught t plus c2 e to the j 2 omega naught t plus everything else up to infinity. Well, we know omega naught, it's equal to 10 pi, so we can just match terms between this equation and this equation over here. What we find is that if we're looking at the minus 1 term, so if we're looking at this, well, this is equal to e to the minus j 10 pi t. We have a term e to the minus j 10 pi t right here. And therefore, the corresponding coefficient, c sub negative 1, must be this whole quantity. Therefore, we can write that c sub negative 1 is equal to 1/2 e to the j pi thirds, simply by inspection between these two equations. Likewise, we can take a look at c sub 1, and we have e to the j 1 times omega naught, which is 10 pi t. So c1 e to the j 10 pi t. And we see that we have a matching term right here. And therefore, we can look at c1 and see that it's this entire term here. And so we can write that C1 is equal to 1/2 e to the minus j pi thirds. And that's it. We can see that there are no other terms here, so every other term in the summation must be equal to 0. So C sub k is equal to 0 for k not equal to plus or minus 1. And that's that. We found every term. Now we can plot this. We can plot this on the omega axis or on the k axis. So let's start with k. And we're going to plot separately the amplitude and the phase. Well, we know that the only place where we have any component is going to be at 1 and -1, and that's going to be at an amplitude of 1/2, since that's that first part over here. So that's 1/2, 1/2, and everything else is going to be 0. And the phase is going to be -pi thirds for the first component and +pi thirds for the negative first component. So something like this, where this is -pi thirds and this is pi thirds, and everything else, as before, is going to be 0 for all other k. And this is for k is 0, 1, 2, 3, -1, -2, -3, just these integer values. We can also look at things in terms of the frequency omega, which is in radians per second as the units. And we can also write those down because we know that the fundamental frequency is 10 pi. We had shown that above. Omega 0 is 10 pi. And we know that each one of these components that we just wrote out is at an integer multiple of the fundamental frequency. So therefore, this is actually, the 0 is still at 0. 1, the thing that corresponds to k equals 1, is at 10 pi. At 2, we have 20 pi. At 3, we have 30 pi, and so on. So we can see what this corresponds to as components in actual frequency as opposed to just the component number of the Fourier series. And the same thing in the phase. As another example, let's look at a signal that is a summation of two cosines as opposed to just a single one. So this is cosine of 2t plus cosine of 3t plus pi over 4. Here we can see that the fundamental frequency is actually not going to be either one of these two because of what we had said earlier. We have to find the periodicity of the overall waveform. Well, if one is going at 2 radians per second and the other one is at 3 radians per second, then the overall waveform is going to oscillate at 1 radian per second because that is the greatest common divisor of both of these. So we can rewrite this once again using Euler's identity as 1/2 e to the j 2t plus 1/2 e to the minus j 2t, that's that first cosine, plus 1/2 e to the j pi over 4 e to the j 3t plus 1/2 e to the minus j pi over 4 e to the minus j 3t. So this is the full expression for both of these cosines. And once again, we can look at it in terms of the series. And let's write out a few of the terms. We know that c sub minus 4 e to the j -4, this is the -4th component, omega naught t, plus c minus 3 e to the j minus 3 omega naught t, plus c minus 2 e to the j minus 2 omega naught t. So these are just complex exponentials at integer multiples of that fundamental frequency that we're adding up. So it's a negative first term plus C0 plus so on. Of course, we're going to have the corresponding positive components as well. And once again, we can just match terms. We can find what these things correspond to because we know that omega 0 is equal to 1. And we can just match terms. So we see that we have something of the form e to the minus j 2t. Well, we have something like that right here too. Because omega 0 is 1, we have e to the minus j 2t. So matching this term and this term, we can see that C2, C minus 2 rather, is equal to 1/2. Well, we can also go to the positive side of the series here, and we'll see that C sub 2 is going to be equal to this part, which is also 1/2. Furthermore, we can match up another term. We have this minus 3 and this minus 3. So therefore we see that C of minus 3 is going to be 1/2 e to the minus j pi over 4. Which means that the positive side is going to be this other component. C3 is going to be 1/2 e to the positive j pi over 4. And that's it. We've accounted for every one of these terms. And therefore C sub k is equal to 0 for k not equal to plus or minus 2 and plus or minus 3. Once more, we can plot this as a function of k, and this is going to be the amplitude, and below it we'll draw the corresponding phase. In this case, we know we have 0 at 0, 0 at 1 and negative 1. At 2, we have an amplitude of 1/2. At 3, we have an amplitude of 1/2, and everything else is going to be 0, and correspondingly on the negative side. So these are points 0, 1, 2, 3, 4, 5, and likewise on the negative side, and so on. And the phase is going to be 0 for 0, 1, negative 1. For 2, it's also going to be 0 because there is no complex component for these values of C2 and C to the negative 2. So that's also 0. For C3, we have pi fourths for C3 and negative pi fourths for C negative 3. And once again, zeros everywhere else. Once again, we can look at things in terms of omega, which is in radians per second, and we know our fundamental frequency is 1, so therefore omega is actually in this case going to be the same as k. It's also going to go 0, 1, 2, 3, 4, but now it's not in terms of just this number, this index k, it's in terms of radians per second. It's just that the fundamental frequency happens to be 1 radian per second. As a little recap of what we had just done with these previous two examples, let's take a look at these plots. So for the first one, we had that x of t is equal to cosine of 10 pi t minus pi thirds. It is just a single cosine. If we look at the plots, we can see that the amplitude of c sub k tells us how much of each complex exponential we have, and the phase tells us where to place it, as I mentioned earlier. So what we see is that we only have components at 10 pi radians per second, which is the frequency of the signal itself, and we have an offset of this pi thirds, which is exactly the offset that we have. Now, this is of course easy to see because our original signal was just this cosine, so of course it's made up of only this one sinusoid at that frequency and that phase offset. For our second example, we saw that we have two cosines that are being added together, one with a phase shift and one without, and looking at this plot of the Fourier series, we can see once again that we have a certain amount of the frequency 2 and 3 radians per second, which is exactly what we have in this signal. We have an even amount of each one. And the frequency at 3 radians per second is offset by pi fourths, which is exactly what we have in our original equation. So we are able to represent this signal as a summation of sinusoids, which it already was to begin with, by using this Fourier series analysis. So this brings me to the last example that I'm going to do, which is not going to be in this nice sinusoidal form to begin with. in this case, we're actually going to draw our original signal and not give it this nice form that we gave before. It's going to look like this, and it's going to be periodic, as it has to be for the Fourier series, at a time capital T. And for these two parts, this is going to be at T1 and this is at T2, and we'll make it symmetric about the y-axis, so it'll be at negative T1 here and negative T2 for this one. And let's give it an amplitude of 1 and 2 for these components. And of course it repeats periodically backwards as well and keeps on going forever. So this is the signal that we're now going to analyze. Our goal, once again, is to represent this signal as a summation of sinusoids. So we know that our c sub k is going to be equal to 1 over t over a period of t, and we're going to choose from negative t over 2 to t over 2 in order to capture this entire signal in here, of x of t times e to the minus jk omega naught t dt. We know also that omega naught is equal to 2 pi over t. As we mentioned, the fundamental frequency is the frequency at which the entire signal oscillates. And we can see that the entire signal repeats after a time of capital T, which means that the fundamental frequency is going to be omega 0 is 2 pi over t. That means that the slowest sinusoid that we're going to use, the lowest frequency sinusoid, is going to have a frequency of omega 0, and every other one has to have an integer multiple of that frequency in order for the summation of all of those, the synthesis, to also have a periodicity that's equal to capital T. So in this case, what we're going to do is we're actually going to plug values into the equation, because we don't have things in a nice form where we can write it directly in terms of complex exponentials. We have to find these values of c sub k by using this equation. So we can break it up into 3 parts, and we're going to look at the integral from negative t2 to negative t1 of 1, since that's the amplitude over here, times e to the minus jk omega naught t dt, plus the next component from negative t1 to t1, and it has an amplitude of 2 times e to the minus jk omega naught t dt, plus the last component, which is from t1 to t2, with again an amplitude of 1 e to the minus jk omega naught t dt. So this is our entire expression, which we have to now evaluate. Notice we didn't, even though we went from negative t over 2 to t over 2, everything outside of this range from negative t2 to t2 is 0, and therefore it doesn't factor into this integration. We could have also included terms that went from negative t over 2 to negative t2 in between here and here, but that's all zeros, and likewise from t2 to t over 2 over here, but that's also going to be all zeros, so it's not part of this. Now we can perform this integration, and what we're going to get is 1 over jk 2 pi times e to the jk omega naught t1 minus e to the minus jk omega naught t1 plus e to the jk omega naught t2 minus e to the minus jk omega naught t2. We can further use Euler's identity on each one of these things to simplify this down to 1 over k pi times sine of k omega naught t1 plus sine of k omega naught t2. And this is the final form that we want to use for our Fourier series. We see that we have c sub k, which is going to be expressed as this, where we plug in values of k and we get out a value for c sub k. And we can see that this is actually going to be a real quantity each time, since we don't have any imaginary components anymore, all the j's canceled out. And so we're left with this as the expression. Now this is not just going to be a finite kind of series as we had before, where we just had a couple of terms. This is actually going to span across all c sub k's. For any value of k, we're going to get a value out of this. We can plot this as we did before on the k axis here for the magnitude of c sub k, and I'm not going to actually draw any of those values, but we can see that they are going to exist at all of these values of k, and likewise for the negative components and so on. And we can draw a similar thing for the phase, which we're going to get from here, but it's going to be zeros and pi, which correspond to positive and negative real numbers. And I'm not going to draw that here, but it can also be derived. More interesting though is to look at the actual frequency omega, again in radians per second. Each one of these values of k is going to correspond to an integer multiple of the fundamental frequency. So we have omega 0, 2 omega 0, 3 omega 0, 4 omega 0, and so on for these values of omega. Suppose we let t, which we left arbitrary in our original formulation, be equal to 5 pi seconds. Then omega 0 is equal to 2/5, and 2 omega 0 is equal to 4/5, 3 omega 0 is equal to 6/5, and so on, all in radians per second. Suppose instead we let t equal 20 pi. So we create a longer period. Then omega 0 is equal to 1/10, 2 omega 0 is equal to 2/10, 3 omega 0 is 3/10, and so on. What we find is that if we change capital T, we change omega 0, and therefore we actually change the true frequency values that each one of these k's corresponds to. The important thing that I'm trying to point out here is that k is just the index of the Fourier series, but the actual frequency content that we're trying to represent is shown by omega, and omega depends on the actual value of omega 0, the fundamental frequency of the signal that we're trying to represent. Therefore, while k is going to stay as just 0, 1, 2, 3, 4 as these index numbers, the true frequency that we're showing changes as a function of omega 0, or equivalently as a function of t, the period of the original signal. Therefore, as we push t further and further out, and we therefore increase t, we decrease omega 0 and actually push each one of these values closer and closer together. And therefore, as we increase t, we actually increase the resolution in this frequency domain, because each one of our points, each one of our values of c sub k is going to be closer together in the frequency axis. Since over here we saw with 5 pi we have 2/5 as each increment, whereas at 20 pi we have 1/10 as each of the increments, which is a finer spacing. And so overall what we have found here is how to represent this signal as a summation of sinusoids. We found that in order to recreate it, we can use our synthesis equation, which we had at the top over here, our synthesis equation, and we use each one of those values of c sub k that we just found a form for, and multiply by the corresponding complex exponential, and add all of those things together. And if we do that for those infinite terms, or a finite amount for an approximation, we're going to get something that resembles this waveform, this signal. And that's exactly what c sub k shows us, how much of each one of those sinusoids is present, and how to arrange them in order to recreate an arbitrary signal. And then we can use that information for further analysis of the properties of this signal. Altogether, we have seen where Fourier series come from and what they mean. We have seen why they are a suitable decomposition of a periodic signal. We have not discussed the use of the Fourier series, but the main idea is that it shows you the frequency content of a signal, which can be very useful for various analytic techniques.